Hi folk, at the end of this video you would be able to understand that how a general purpose I/O can be implemented via multiplexed I/O and extended multiplexed I/O in Zynq 7000 AP SoC. So today's agenda has basically three parts. In the first part, a theoretical explanation of I/O peripherals, GPIO, MIO, EMIO will be given. In the next part, GPIO via MIO will be implemented in Vivado and will be tested on Z-board. In the last part, again GPIO via EMIO will be implemented in Z-board. Okay, so basically this is a very general diagram of I/O peripherals communication with PL and external world. This diagram is taken from UG 585. You can download this document from internet. It is very useful. We will use this document frequently. Okay, so I/O peripherals has basically two interfaces, one on right side, other one is on left side. On the left side we have AHB and APB. AHB is a high speed, high data rate bus protocol, and APB is a low data rate bus protocol. Since I/O peripherals are of different types, some needs high data rate like Ethernet will be communicated with processor via this bus protocol. Others needs low data rate like UART will be communicated with processor via this bus protocol. On the right side, these I/O peripherals can be routed to PL via EMIO or can be routed directly to the external world via MIO. This is a very detailed diagram of I/O peripherals. Again, it is taken from UG 585. You can download it from internet. So here we can clearly see that some of I/O peripherals are directly only connected to MIO, others are only connected to EMIO, and rest of I/O peripherals can be connected to MIO or EMIO. For example, UART can be connected to via EMIO to PL, or it can be programmed via MIO. For example, again USB, where is USB? Yeah, USB can only be routed via MIO. It cannot be routed to PL. In the same way, QSPI can only be routed to MIO. Again, if we see here, high USB is a high data rate I/O peripheral, so it will be communicated with PS via high data rate bus protocol. It also have APB bus protocol, but this low data rate bus protocol is used to configure USB. If we talk about low data rate applications, I/O peripherals like UART they are directly communicated with the PS via low data rate bus protocol, APB. So in this part our focus will be on this portion. We will be explaining and implementing this part. So here we can see that there are 4 different banks, bank 0, 1, 2, 3. It is really important to note, to remember, to memorize that GPIO banks are GPIO banks registers 0 and 1 can only be routed via MIO, and GPIO banks 2 and 3 can only be routed via EMIO to PL. Okay, so we have a basic understanding how IO peripheral controller works and how they are connected with the PS, which bus protocols are there. Now we will have insides of GPIO and MIO, then EMIO. So again, this diagram is taken from UG 585. If we have a cross section of MIO, we will have this structure resides inside of MIO, multiplexed IO peripherals. So basically in Zynq 7000 we have 54, as it is written here, cross 54 MIO pins, and each pin can be independently programmed, and each pin has 32-bit register to configure the pins. So the pins can be configured as input, can be configured as output, and it also have different level of mux. So basically MIO has 4 level 0, 1, 2, 3. Why we have different levels? Because some IO peripherals have high data rate, so we can directly route them by using level 0, and we will bypass these levels. In other IO peripherals which requires low data rate like UART or GPIO, we can route them via all these 4 levels. Okay, so GPIOs are available for each MIO peripherals. So this is what we have MIO, how MIO works. I have explained here. So we can configure, as I mentioned, we can configure MIO via MIO pins. These are MIO pins from 0 to 53. These are basically registers, and these registers values can be again founded, can be found in UG 585. So at the very beginning I have given a very basic idea of MIO, then I have given the insides of MIO. Now I will tell you how to program MIO. Then next I will tell you how to program GPIO. So after learning the basic idea of MIO and GPIO, it would be easy for us to program GPIO via Vivaro. So as I mentioned that each MIO pin, which are 54 in total, has an address, has a register for each pin. So for example, I have taken an example of MIO pin 00. This is for 0 pin configuration. So this is a 32-bit register. Again, it is taken from 585. The address of this pin is this is the address of this pin, 32-bit address 00000700. So this is a relative address. Relative to what? Relative to base address. This is a base address of SL, status level control register. So if we write 32-bit data on this register, it will configure MIO pin 0. So 32-bit, this is a 32-bit data, how we can configure this pin. So it has try enable. If you want to enable a try state, you can write 1 here. Again, as I mentioned, there are 4 different levels for muxing. Level 0, 1, 2, 3. You can select them according to your application. For speed, you can have a slow speed for slow data rate application, high speed for high IO peripherals applications. We also have IO types. It can be 1.8 volt, 2.5, 3.3 volt. You can configure according to your application. Pull up, I always recommend you always enable this pin, because if you do not enable this pin, you wouldn't be able to say anything about the outputs. So if you enable it, pull up, the output will remain in high state. In other case, the output will be floating, so you cannot predict anything. So I have given an example here. Let's suppose we want to configure MIO pin 0 as a GPIO signal. Then we need to select, because GPIO is a low data rate IO peripheral, general purpose IO peripheral. Then we need to use all these 4 levels. Write 0, set, try, enable. We don't need to enable, we don't want to control this state, and select 1.8 volt, slow CMOS, again low data rate. Pull up resistor, yeah, enable it, and disable HSTL. So we have learned how to program MIO. We will do programming while we will be implementing GPIO. So we have a basic idea of MIO, then we have insides of MIO, then we had an example of MIO, how to program an MIO. Now we have a GPIO. Basically we have 4 different GPIO banks. As I mentioned at the very beginning of the lecture, GPIO 0 and 1 bank are being programmed or controlled via MIO. They cannot be routed to PL. Bank 2 and 3 can only be routed to PL via EMIO. So as we know that MIO has only 54 pins, therefore bank 0, 32 bits are directly connected with the first 32 MIO, can be programmed to first 32 MIO, and it is not 32 because it is 32, but the remaining bits are useless because MIO has 54 in total pins. So the remaining 22 pins are connected with the remaining MIO pins. But this is not a case in banks 2 and 3. All the 32 of both banks are useful. So we have 64 pins here and 54 pins here. As MIO pins has configuration, and the configuration of MIO pins could be done via different registers. In the same way, these banks also have addresses and they can be configured. So again, these banks has relative address relative to some base address, and this is the base address of these banks. So again, bank 0 control 0 to 31 MIO pins, 1 control 32 to 53, 2 control 0 to 31 EMIO, and bank 3 32 to 63. Yeah, we had very basic idea of GPIO. Now we will have a more detailed form of GPIO as we had for MIO. Yeah, so these are the basic registers. These are the basic registers to configure GPIO. If GPIO can be configured as interrupt, or they can be configured as normal input and output. If you want to configure them as normal input and output, you will be playing with these registers only. Each of the register is 32-bit. Okay, so 32-bit, and each bank has their corresponding 32-bit register. Like for bank 0, GPIO bank 0, these are the registers for each bank. Each bank has a complete set of these registers. So okay, so let's have a very brief idea how and what are the functions of these registers. So direction M register is used to control the direction of GPIO. Either it is configured as input or output. IO enable, so output enable. If the GPIO is configured as output, then you can enable and disable GPIO via using this register. Data, if the GPIO is configured as output, the data that should be written to the output port will be written on this register. If you want to read the GPIO's status, I mean if you have configured GPIO as an input, you will be reading data from these registers. So all these registers has again addresses which are mentioned in again UG585. So this is when you are working in normal IO mode. What if the GPIO is configured as interrupt, I mean state? Yeah, in this case you will be playing with these registers. So interrupt type, either the interrupt is level or edge type. Interrupt polarity, so if the level is a low level or high level, if the if it is edge trigger, the level can be positive, the edge can be a rising edge, or it can be falling edge. All these things are configured here. Int any, interrupt any means so what if this register is used to configure pause edge or nag edge? What if we want to have an interrupt on both edge? So if you want to configure and if you want to have an interrupt on both edge of a clock or a signal, I mean rising edge and falling edge, you can do via interrupt any. So these are used to configure interrupt level or edge trigger. So this register is used to interrupt enable. Interrupt enable, if you want to enable an interrupt, you will be writing 1 in this register, 32-bit again for each bank. Interrupt disable, to disable the interrupt. Interrupt mask, you will be able to read by reading this register, you would be able to see which bit of bank is configured as interrupt and which one is masked. So let's have a very quick overview how the interrupts work. So if interrupt occur, it will go to interrupt detection logic. Will be that logic will be generated based on these three registers, and that interrupt will go to interrupt state, and it will interrupt. That interrupt is ended via this signal. If we have an interrupt enable, the interrupt will go to general interrupt controller, and that general interrupt controller is connected with the processor directly, and the interrupt request that is specified in Zynq 7000 SoC for GPIO is 52. We will be using this 52 interrupt request while we will be implementing GPIO. Okay, if we have an interrupt, that interrupt can be read in interrupt status register. If interrupt occur, and we can easily see the interrupt status by writing 1 to this interrupt status register will clear the interrupt. Yeah, so we have again a good idea of how a GPIO works. So in each GPIO bank we have all these sets of registers. We will be programming all these registers while we will be playing with GPIO in next part of the video. So this is a very basic programming guide, like as I have given a programming guide for MIO. Basically we wouldn't be playing much with MIO programming. We would be playing with programming of GPIO when we would be working on GPIO. So please listen it carefully. So GPIO programming has basically 3 parts: GPIO configuration, write data, read data. Configuration, again, I have given an example. For example, we want to configure GPIO pin 10 as an output. So as GPIO pin 10 comes or belongs to bank 0, then as I said, each bank has a complete set of these registers. If it is bank 0, then DIRM 0, DIRM 0, this had a base address plus relative address. On that address we will write this value. It will enable, set the direction, it will set the direction of this pin as output. Again, set output enable OEN underscore 0, OEN underscore 0 for bank 0. We will write this value on this address. The value of this address can be found in, again, UG 585 document. Okay, we have set pin 10 as output, and we also enable it. We can write no data on this pin. Read, modify are, so there are 2 ways to write data on this pin. The first way is you can write directly 32-bit. So what will happen in this case? Okay, we would be able to write on this pin, but the remaining pin will also have a data. So it is not desired, because we just want to play with this specific pin. We don't want to change the data of other pins. So we can do that as well. Zynq 7000 SoC has given this opportunity to us. We can do it via masking. So by using masking we are able to write a data on only one or more pins without disturbing the remaining ones. Okay, we have two ways to write a data on GPIO pins. In the same way, while we will be reading a data from GPIO pin, we can directly read our data from data RO, read only. Yeah, here data RO, because yeah, underscore X represent to the bank. Bank can be 0, 1, 2, 3. R as it we can directly configure is as a normal input, or we can configure it as interrupt. If we configure it as interrupt, we will be doing the following things. We need to, like in this example, we set the trigger as a rising edge, write 1 to interrupt type, yeah, as it is 32-bit again. If we configure MIO pin 10 as a rising edge and write 1 to interrupt polarity, it means if we write a 1, it means pos edge. Write 0 to interrupt any. If we write a 0, it means it will not be triggered on both edge. Enable interrupt, we just enable interrupt. Yeah, here enable interrupt. Right. Okay, interrupt is enabled. We will be checking interrupt status. If it is 1, interrupt even we can do anything here on interrupt occurrence. After have a desired functions, we can disable interrupt by writing 1 to the GPIO. Yeah, so we have a very good idea about GPIO and MIO. We have a good theoretical idea about GPIO banks, about their registers, and a very basic idea how to program them. In the next part of the video, I will implement GPIO via MIO, and then I will show you how these registers that I have explained in this video can be programmed. Okay, thank you very much for watching this video, and very important, don't forget to subscribe and share my channel, because sharing is caring. Good luck.